Welcome back to Bite-Sized Breakthroughs, the podcast exploring the latest and greatest in the world of AI. Today, we're diving deep into a fascinating paper that bridges the gap between supervised learning and reinforcement learning, showcasing how transformer models can learn in-context decision-making. Joining us is Dr. Paige Turner, a leading researcher in this field, and Prof. Wood Spectrum, a renowned expert on the broader implications of AI. Dr. Turner, thank you for joining us.
Thank you for having me, Alex. I'm excited to discuss this cutting-edge research.
Prof. Spectrum, it's always a pleasure to have you on the show. Your insights on the wider impact of AI are invaluable.
The pleasure is all mine, Alex. I'm eager to see how this research fits into the bigger picture.
So, Dr. Turner, let's start with the basics. What is the primary focus of this paper? And can you give us a bit of historical context?
Sure. The paper focuses on in-context learning and reinforcement learning, RL, specifically using transformer models. This is a relatively new approach that utilizes the powerful in-context learning abilities of transformers, which have excelled in natural language processing. Historically, RL algorithms often rely on extensive trial and error to learn optimal policies. This can be slow and data-intensive, particularly for complex environments. Transformers, by contrast, can learn from just a few examples, making them attractive for tackling complex tasks quickly.
So, in essence, we're looking at ways to make RL agents more efficient and adaptable.
Exactly, Alex. This paper introduces a new method called Decision-Pretrained Transformer, DPT, that utilizes supervised pretraining to equip transformers with the ability to make decisions in new RL environments based on a small set of examples. It's essentially learning to learn.
That's quite intriguing. Can you elaborate on the key contributions and innovations of this paper?
Certainly. The paper's core innovation is DPT, a supervised pre-training method that teaches a transformer to predict the optimal action for a given query state, considering an in-context dataset of interactions from the current environment. This dataset could be generated from random interactions, expert demonstrations, or even rollouts of an existing algorithm.
So DPT learns to make decisions based on contextual data without needing to update its parameters when placed in a new environment. It's essentially learning a decision-making strategy.
Precisely. The surprising thing is that DPT, despite not being explicitly trained for exploration or conservatism, exhibits both behaviors in new environments. It implicitly learns to navigate the trade-off between exploring new possibilities and exploiting known information.
That's fascinating. Can you give us a concrete example of how this works?
Imagine a multi-armed bandit problem, where you have several slot machines with different reward probabilities. You don't know the probabilities beforehand. DPT, trained on various bandit configurations, can be given a small dataset of interactions with the current bandit. Even if the data is noisy and doesn't reveal the best option, DPT can still reason about uncertainty and learn to explore, potentially discovering the best machine to pull.
So it's not just about predicting the best action based on the available data. It's about learning how to learn in a new context. And it's doing this without explicit training for those specific behaviors, like exploration.
That's right. It's like DPT is learning the fundamental principles of decision-making, enabling it to adapt to different scenarios effectively.
Prof. Spectrum, your expertise on the broader context of AI is invaluable. How do you see this research impacting the field?
This is groundbreaking work, Alex. It challenges our assumptions about how we train RL agents. Traditionally, we've focused on designing algorithms that explicitly handle exploration and exploitation. But this research shows that we can potentially achieve these behaviors through implicit learning, which could revolutionize how we design RL algorithms.
It's essentially teaching the agent to think like a human by learning from experience and adapting to new situations.
Exactly. And this has huge implications for real-world applications. Imagine robots that can quickly learn to perform new tasks in unfamiliar environments, or personalized healthcare systems that can adapt to individual patient needs. This research opens the door to developing agents that are more robust and efficient, capable of handling unforeseen challenges.
This is really fascinating. Dr. Turner, could you delve deeper into the methodology of this paper? How is DPT trained, and how does it differ from existing meta-RL methods?
Certainly. DPT's training involves a couple of key steps. First, we collect a diverse set of in-context datasets. Each dataset consists of interactions from a specific RL environment, like the bandit example we discussed earlier. We also include the query state, which is the state for which the model needs to predict the best action, and the corresponding optimal action. This collection of datasets, query states, and optimal actions forms our pre-training dataset.
So the model is learning from a diverse set of environments, capturing a wide range of decision-making scenarios.
Correct. Then we train a transformer model, like the GPT-2 architecture, on this pre-training dataset. The model learns to associate elements of the in-context dataset through its attention mechanism, capturing the relationships between actions and their outcomes. The key here is that it learns to predict the optimal action based on this contextual information.
This is similar to how transformers work in NLP, where they learn to predict the next word in a sequence based on the preceding context. But in this case, we're predicting actions instead of words.
Exactly. And once DPT is trained, we can deploy it in new RL environments. Given a query state and a dataset of interactions from that environment, DPT can make predictions about the optimal action without needing any further parameter updates. It's essentially using its pre-trained knowledge to adapt to new situations.
So DPT is learning a decision-making strategy, not a specific policy for each environment. That's a key difference from existing meta-RL methods.
You're right, Alex. Existing meta-RL methods often focus on learning task-specific policies or learning to adapt parameters of a neural network policy. DPT, by contrast, learns a more general strategy for making decisions, enabling it to adapt to new environments without retraining.
Professor Spectrum, could you comment on the significance of this difference from a broader perspective?
This is a crucial distinction, Alex. By learning a decision-making strategy, DPT transcends the limitations of learning specific policies for each environment. It has the potential to be more versatile, capable of handling a wider range of tasks, and adapting more effectively to new situations. This is essential for creating truly intelligent agents that can navigate complex, ever-changing environments.
So DPT is essentially learning a meta-algorithm for decision-making. That's a huge shift in how we think about training RL agents.
Indeed. And the paper also provides strong theoretical evidence to support these findings. They demonstrate that DPT can be viewed as an efficient implementation of Bayesian posterior sampling, a provably sample-efficient RL algorithm. This connection offers a theoretical foundation for DPT's performance and suggests a promising path towards developing practical and efficient RL methods.
That's quite a mouthful. Can you break down the concept of posterior sampling for our listeners? It sounds pretty technical.
Certainly. Posterior sampling is a Bayesian approach to RL. It involves maintaining a distribution over possible models, like the reward functions in a bandit problem, and updating this distribution as you gather new data. When making a decision, you sample a model from this updated distribution and execute its optimal policy. This approach has strong theoretical guarantees, but it can be computationally expensive.
So DPT, by learning to predict optimal actions, is implicitly performing posterior sampling. That's quite remarkable.
Yes, that's the key insight. DPT, through its pre-training, is learning to represent the posterior distribution over possible models. This allows it to make decisions efficiently without having to explicitly compute and update the posterior at each step.
Professor Spectrum, how does this theoretical connection to posterior sampling add to the significance of this research?
It's a game changer, Alex. Posterior sampling has always been a theoretical gold standard, but its computational complexity has made it impractical for real-world applications. This paper offers a compelling solution by demonstrating that we can achieve the same results through a simple, supervised pre-training method. This could unlock a new era of practical and efficient Bayesian RL.
That's very insightful. Dr. Turner, can you walk us through the experimental setup and the results that support these findings? I'm particularly interested in the comparisons to other methods.
Of course. We evaluated DPT in both Bandit and Markov Decision Process (MDP) environments. For Bandits, we compared DPT against classic algorithms like UCB and Thompson sampling, highlighting DPT's ability to match their performance in online exploration without explicit training for that behavior. In the MDP settings, we compared DPT with algorithm distillation, AD, which distills traces of an existing RL algorithm into a task-agnostic model, and RL2, which learns to adapt a policy based on the given context. DPT consistently outperformed or matched the performance of these existing methods, demonstrating its effectiveness in both offline and online settings.
So, in those experiments, DPT not only learned to explore and exploit, but it also generalized to new tasks and even outperformed the algorithms used to generate its pre-training data. That's quite impressive.
Yes, Alex. In one experiment, DPT was trained on linear bandit problems, where the reward function is linear in some unknown feature representation. The data used for training was generated by Thompson sampling, which doesn't explicitly leverage that linear structure. Yet DPT was able to learn to exploit this hidden structure, achieving performance close to LinUCB, an algorithm designed specifically for linear bandits.
That's incredible. It's like DPT is learning to discover and exploit hidden patterns in the data, which is a crucial ability for intelligent agents.
Absolutely. And these findings are not limited to simple bandits. In the darkroom environment, a 2D grid world where the agent needs to find a goal, DPT demonstrated strong performance both offline and online, surpassing AD and RL2. It also generalized to unseen goal locations and even adapted to new action permutations, demonstrating its ability to handle complex tasks and unexpected changes.
So DPT is not just good at exploring and exploiting, it's also remarkably adaptable. This is a major breakthrough for the field of RL.
Indeed. And the paper even tested DPT in MiniWorld, a 3D visual navigation environment with image-based observations, showing its scalability to high-dimensional problems. The model was able to find the correct target box, even when the color of the box was unknown. These results highlight the broad applicability of DPT across different domains and sensory modalities.
Prof. Spectrum, this research seems very promising, but are there any limitations or challenges that need to be addressed?
Certainly, Alex. While this research is incredibly promising, it's important to acknowledge some limitations. The paper highlights that DPT requires optimal actions during pre-training, while they show that this requirement can be relaxed by using actions generated by another RL-trained agent. Further research is needed to understand how to best leverage multitask decision-making datasets. It's also worth noting that the practical implementation of DPT in MDPs deviates from the idealized theoretical model of posterior sampling. Bridging this gap is a critical challenge for future work.
So it seems there's still some work to be done to make this approach truly practical, but the potential is certainly there.
Absolutely. And the paper also outlines several promising directions for future research. One key area is exploring the use of DPT with different task distributions during pre-training, aiming to improve its generalization capabilities to tasks outside its original training distribution. Another area is investigating the potential applications of DPT to existing foundation models, which are increasingly being deployed in decision-making settings.
That's exciting. It seems we're on the cusp of a new era in RL, where agents can learn from data and adapt to new environments more effectively than ever before.
Indeed, Alex. This research represents a significant leap forward in our understanding of how to equip transformers with decision-making abilities. It demonstrates the power of supervised pre-training for RL and opens up exciting possibilities for developing more intelligent and versatile agents.
Professor Spectrum, any concluding thoughts on the potential impact of this research?
This research is a testament to the transformative potential of AI, Alex. It's a reminder that we're constantly pushing the boundaries of what's possible with these technologies. The ability to train agents that can learn in context and adapt to new situations holds tremendous promise for addressing complex real-world challenges in fields such as robotics, healthcare, and finance. This is a research area we need to continue to explore and develop, as it has the potential to revolutionize our lives and create a more intelligent and adaptable future.
Well said, Prof. Spectrum. Dr. Turner, thank you for sharing this groundbreaking research with us. Your insights have truly illuminated the potential of this new approach to RL. And thank you, Prof. Spectrum, for your insightful perspectives on the broader implications of this work. For our listeners, remember to stay curious and keep exploring the ever-evolving world of AI. This is Alex Askwell signing off for Bite-Sized Breakthroughs.